Welcome back to our class. This is our sixth lecture of Math405. We started last time talking about section 1.5, orthogonal matrices. And today we'll carry on and we'll continue with section 1.6 about eigenvalues and eigenvectors. So this is the outline of the course slides regarding section 1.5 and 1.6. We talk here mainly about orthogonality, singular vectors, projection, rotation, and reflection, eigenvalues, and eigenvectors. So I'll be quickly reviewing what we did last time. We said that orthogonality means perpendicularity in general mathematics. And here it is extended beyond the notion of angle between vectors. Two orthogonal vectors, x and y, should have their product equal to 0, or one can say their scalar product equal to 0. For orthogonal basis for a subspace, every pair of vi and vj is such that we talk here about every pair of vectors vi and vj such that their product or scalar product is equal to 0 again. Orthonormal base, what does orthonormal mean? Orthonormal means they are orthogonal and they both have unit normals. For orthogonal columns, here we call them thin, tall columns. Q are those who had satisfied this condition that QT times Q equals R. Orthogonal matrices are square matrices with orthonormal columns obtained with orthonormal columns. And they do generally satisfy this condition that QT is equal to Q minus, Q inverse. So let's take this example where x equals 1, 2, 2, and y is 2, 1, minus 1. So you can check that the scalar product here, x, t, y, is equal to 0. So the two vectors have, they are orthogonal, and they do define what we call a right-angled triangle, with hypotenuse that could be given by x minus 1, for instance, minus 1, 1, 4. In the R3 space, you can consider R, J, and K, 1, 0, 0, 0, 1, 0, 0, 0, 1, respectively, defining what are an orthonormal basis. So they could possibly generate any member of the R3 space. We talked about what we call Hadamard matrices, which contain orthogonal bases in R square, R4, or R8. For example, this one, the first one here is the Hadamard matrix in R2. The next one is the Hadamard matrix in R4, and the last one is a Hadamard matrix in R8. And you can all check that the product of each pair of columns here is equal to 0. Okay? So we talked about that last time. And then we started talking about how come subspaces could be octagonal columns and matrices could be orthogonal. So, for example, you can check that if you consider the row space of A, for those who've been following us from the beginning, can you remind us what is a row space, guys? What is a row space of a matrix?
The columns of A transpose.
Yeah. So it's the column space of the A transpose. I mean, all the set of independent rows in A, or all the set of independent columns in A transpose. So we say here that the row space of A is orthogonal to the null space of A. What does that mean? So if you multiply any row in A by x, you should have 0. And this is exactly the definition of the null space, in fact. Okay? So every row of A multiplied by x should give you 0. That's why you have a whole column of zeros at the end. For the column space of A, it's also orthogonal to the null left, or to the null space of A, or what we call the null space of A transpose. And here again, you can check that if you take the left null space of A, or the null space of AT, basically you're multiplying every column of A by y, and which means ATY equals 0, and that's it. So you have now the proof that the column space of A is orthogonal to the left null space, or what one can call also the null space of AT. So just for, from a general representation, you can see in this figure here that the null space of A is grown to be orthogonal to space of A. So they kind of belong to two orthogonal planes, if you can imagine. And similarly, the null space of AT, or the left null space of A, is orthogonal to the corner space of A. Okay? So for example, here they're saying that, let's say that the dimension here of the row space is R, and the dimension here they're working here in Rn. So basically, why do they work in Rn? Because they're saying they do have n rows in A. Okay? And here similarly they working in Rn because they're saying that they have n columns. Okay. So that's just to give you a quick idea. So basically you have subspaces which are orthogonal. Now about the single vector decomposition, we said that it is a very important theme, in fact, or theorem in data science, or what we call SVD, single vector decomposition. Well, what it does, it finds orthonormal basis, V1 to VR for the row space of A, and U1 to UR for the column space of A. And since we said orthonormal, it means that they should be orthogonal and have unit norms. So the special cases from the SVD have the extra property that each pair V and U is connected by A. So for example, if you take the pair V1, V2, V1, U1, you can see that AV1 should be equal to sigma 1 U1. Similarly, AV2, sigma 2 U2. So basically, you can say that A takes any orthogonal basis of V to an orthogonal basis of U. Okay? So if you multiply A by any V, you obtain a multiple of a component of the U basis, basically. Okay, so one way is kind of one way to move from a space to another space, or a subspace to another space. Okay, so that's why we talk about singular vector decomposition. Now, to follow this idea, let's say this. Let's consider these columns, for instance, and these columns, they have the basic property that they offer a condition that they can always compose what we call orthogonal matrices. For example, if you take the first column Q1, which is equal to 1/3 to -1, and or the matrix Q2 obtained here, or Q3. Well, if you take any of these matrices, you can check that for every one of them, Qt times Q is equal to R. Okay? So basically, if you multiply Q1 by its transpose, what you can have is that you're going to have 4 plus 4. Yeah? Let me write it here. So if you multiply Q1 transpose by Q, what am I going to have? I'm going to have 1/9. I'm going to put it outside. I'm going to have the 2 to -1 that multiplies the 2 to -1. Okay? So basically, I'm having a single scalar, which is 1 here, okay? Which is the identity matrix, the set of real numbers. So I'm going to have 1/9 divided, multiplying 9, basically, which is just 1. Okay? Okay? So now, but if I take Q2 times its transpose, or Q2 transpose times Q2, I can leave the 1/2 times 1/2 outside, so basically I'm going to have 1/4. And I'm going to place the transpose matrix, which is 2 to -1. Okay? And I'm going to multiply by my matrix Q2. So I have 2 minus 1, 2 minus 1, 2. Okay. So let's check the first element. The first element I'm supposed to have here, what I'm going to have. This one should have been 1/9. Sorry for that, guys. So I'm going to have, of course, the same item I had when I multiplied Q1 by Q1. So I'm going to have 4 plus 4 plus 1, which is 9 divided by 9, which is 1. Then I'm going to have 2 times 2, which is 4, minus 2, which is 2, minus 2, which is 0. Why is that happening, Shabab? Can you tell me why is that happening? Why the result when I multiply the first row of Q transpose by the second column of Q2 gives me 0? What does that mean, basically?
Vertical matrix.
The columns are vertical, are orthogonal, right?
Yes.
The columns in Q2 are orthogonal. You can check that these two columns are orthogonal. They're not only independent, but they do form an orthogonal basis in R2, if you wish. Okay, so you will have in R2. Am I right? This should have been R3. So they are orthogonal here, and their product gives you 4 minus 2 minus 2, which is 0. So again, well, basically you're doing just the opposite, the other way. So when you multiply 2 by 2, which is 4 minus 2 minus another 2, so you get the 0, and basically you get the I. So we're able to verify at least the condition that these special matrices, they do satisfy the condition that the Q transpose times Q always gives I. So as you just said, Khalid, if I'm right, in fact, here, these matrices are not supposed to be squared. So we can not talk about the inverse. Okay? They're not what one can call invertible matrices, because in general, they are not squared. But they do satisfy this condition that QT times Q equals I. So there is one way to get from them matrix that, when multiplied by our matrix Q, gives I. So notice also here that for every matrix divided by Q times Qt, you'll always have P squared equals P. Why is that happening? Because when you place, if you place QT again, so when you try to compute P squared, you always end up removing part of it, which is in the middle, which is the one you could obtain when you multiply the Qt by Q, which gives you I. Okay? So basically, what you get here is finally QQT, which is again P. Okay? So P squared is nothing but P. And this signals what we call, in general, the projection matrix. So for instance, if P squared is equal to P transpose, then whenever you multiply P by a column B, you obtain what we call the orthogonal projection of B onto the column space of B. Okay? So, we are working on R3. When you project a line on a plane, you get another line which belongs to the projection plane. Okay? So, it is referred to using a different vector, of course, which is the projection vector. So here we're talking about projection. So we consider that we have this vector B, 3, 3, 3, and we are considering that we are projecting it on the Q1 line. So if we multiply it by Q1, the matrix obtained from Q1 performing the product by Q1T. Okay. So we obtain 1/9. Which is the P1 matrix, which is here, sorry, should have been here. So this is the P1 matrix. Multiplying B, it gives you, in fact, this portion. When if you see under the curve and the representation, you see that this is B here, which is 0, 3, 3, and projected orthogonally on the line 2, 2, negative 1. It gives you this part. Now, what about the remaining part? This is an information which is lost, and we call it error here, which you could easily obtain it if you want to complete the Pythagoras theorem, or if you want to just to work on it. So we can easily obtain the error, which is given by 114. It has norm equal to square root of 18. And the second example, we are working with B, which is again 333. Okay, and in this case, what are we doing? We are projecting on P2 using P2. So we are using the other matrix Q2 we defined earlier in the previous slide. Okay, and we obtain this vector, which is Q2 P2B, which is here for 1, 1. Okay, and the error is that part, the information loss. Okay. So this is to give you an idea how these what we call orthogonal matrices could be useful when we are trying to move from to project on a plane or on a vector on a line. This is what could happen. So we almost stopped here last time. So that was about projection. But as you know, in geometry or in real life, we don't only use projection. We can have also rotations. Okay, so one can think which kind of matrices could give me a rotation. So we start by a common observation is that when the whole plane rotates around the origin, lengths don't change, of course. Okay, so the angle between vectors shouldn't change. The angles between vectors, they shouldn't change. So if you consider the columns of Q here, for instance, define it this way, where Q rotate is defines it satisfies the orthogonality condition, but they're given by cosine theta sine theta and minus sine theta cosine theta. Okay, so if you take two vectors here, for instance, 1, 0 and 0, 1. And multiply each one by the Q rotate, you obtain the new vectors, right? You see here. These are the resulting vectors. And you see the angle, which was 90 degrees at the beginning, is still the same. Got it, Shabab? Okay? So it's somehow, mathematically speaking, what you could obtain if you rotate a picture. Okay? So imagine you're just simply using your mobile, and you took a picture and you just observed that you didn't take it in the right angle. But instead of taking a landscape, you took a portrait or something like this and you want to rotate it. In fact, algorithmically, this is what is happening inside with the software to rotate your picture. Okay? Each point or dot in the picture is rotated this way. Okay? So this is counterclockwise. It could work counterclockwise. It depends on the rotation matrix you consider. Okay. So fundamentally speaking, when you talk about image recognition or image retreatment, fundamentally it's all based on mathematics. So this is for the rotation. Again, more than rotation, we can have what we call reflection. Imagine you have a mirror. So if you multiply a column by -1, the two columns are still orthogonal. I mean, if you multiply the columns of what? Of the Q rotate we had before, but they give what we call the reflection through the line theta over 2. Okay, so if you multiply by the following Q reflect matrix, you obtain a reflection, in fact. Okay, so for example, you had before this. These are my two vectors initially here, the one I dashed, Shabab. Okay, so if you multiply them, and this is the line theta over 2. Okay, so for the figure, imagine this is R3. We are working on R3. Okay, and the theta over 2 is here over here. So if you multiply by the Q reflect, you obtain the two new vectors, the one that is here and the one that is here, and of course there is a preservation of angles. Okay, and one can observe that reflection times reflection here is equal to rotation, and rotation times reflection gives reflection. Okay, so this is a common and general result, which is no. Right. So what is important, or what is interesting, let me say, is that we can define projection matrices, rotation matrices, reflection matrices using simple orthogonality properties on the columns of matrix. Right? Okay, so let me carry on now with a new material. Well, the new material tries to dive in the notion of eigenvalues and eigenvectors we talked about previous time. And for those who have taken, for example, Math405, which is differential equations and linear algebra, or Math405, linear algebra, or previous courses somehow in linear algebra, they give some very interesting and some very bright notions about eigenvalues and eigenvectors. Here, from our perspective, from our point of view in data science, we try to give another way to see things. Okay. First of all, we go to the basics. What is the definition of an eigenvalue? What is the definition of an eigenvector? We try to see how interesting they could be when it comes to treating data, to refining data, to explore data, perform what we call data mining. So, what is an eigenvalue? Well, it's commonly understood that an eigenvalue is a solution to the following equation, where you have the determinant of A minus lambda I equals 0. I think pretty well everyone understood that before. So you can imagine, like if you go back to the simple rules of mathematics, you're obtaining an equation. Well, it has some degree, a polynomial equation. So basically, you could have 0 roots, you could have repeated roots, you could have real roots, you could have also complex roots. Hopefully, you agree with this. So problems might happen, computationally speaking, and it's not fun at all, even for very skilled mathematicians, and let's waste time. It's not fun at all to try to solve every single polynomial equation. This is not the purpose of, or the goal or the intention of any mathematics course. The most important thing is to understand the concept. Here, we also review what we call an eigenvector. So for every given solution to the previous equation, where the determinant of A minus lambda I is equal to 0, we define an eigenvector x such that AX should be equal to lambda x. So basically speaking, eigenvectors, they don't change the direction when we multiply them by A. AX equals lambda x. So when you multiply the A by x, you do have lambda x. They don't change the direction when you multiply by A. So we can move a little bit forward. And if you try to multiply again by A, like here, it means you can just here expand it, and you can write it as A times AX, where the part in the middle here comes to be equal to lambda x again. And since lambda is supposed to be a real number and not a matrix, because the eigenvalue is a number, whether a complex or real number, you can bring it outside. Okay, which means that you could obtain here again lambda x. So at the end of the day, what you could observe is a squared x is equal to lambda squared x, which means that, in fact, x is also what? An eigenvector for a squared matrix. Okay? So if you consider the a squared matrix, x would be also an eigenvector to it, because it does satisfy the property we communicated on eigenvector, but now for just a squared. So most n by n matrices, Shabab, have independent eigenvectors. And x1 to xn, just to notice the fact that they could be, most of the time they are independent, with possibly n different eigenvalues. So to every lambda corresponds an x. So for every eigenvalue corresponds an eigenvector. So in that case, if you are working in Rn, suppose every n-dimensional vector v, well, it could be expressed as a linear combination of the eigenvectors you obtained from the matrix, right? Okay. If you are saying that the vectors are independent, well, it could be used as a basis, and you can basically generate every single vector component of your Rn space. Okay. So what we we should signal here for the eigenvalues and the eigenvectors is that in fact eigenvalues, they look into the heart of a matrix. So we just said that they could be used to generate every single component of this subspace, first of all. And if you multiply, for instance, V, which was obtained in the previous slide, by A, so A times V, could give you the following. Why is that happening? Because you just said that A could be summarized as AX equals lambda X. Okay, so if you multiply here, you come here and multiply A by V, well, you just happen to obtain again the occurrence of C multiplying lambda X. Okay? Is that clear, Shabbat? So since V is equal to Cx, let's say Cx, okay? So if you come to multiply the A by V, it's like multiplying AV times ACX, okay? Right? And from here, you can insert the lambdas. So AV equals, in fact, to the linear combination of C1, lambda 1, X1, and so on. Okay? And you can perform this even k times, you always have the following. Okay? And you see the only thing that changes is the power above the eigenvalues, which is very interesting because it is telling you that if your component is weak, when you raise it to the power k, it should go to 0. If one of the components here is weak from the beginning, if the eigenvalue is very small, it means when you raise the matrix to some power, this should go to 0. And if the component of the eigenvalue is quite large, it should go to a very large value when you raise it to the power k. So this is the observation we are adding here. If the absolute value of lambda 1, for example, is larger than 1, then the component C1 lambda 1 to the power n, when you take the power, will grow as n increases. While if you take, for instance, the absolute value of lambda 2 less than 1, then that component will be steadily disappearing if you take the highest power. Okay? So, not to bother you that much, so let's try to work on this matrix. Okay? So, here we are announcing that we have the eigenvalues. Okay? So, let me just a little bit work the math behind the fact that we had this eigenvalue, these eigenvalues. So, I'm sharing with you now. I'll be sharing the whiteboard, and we try to verify at least from the beginning that we do have the right eigenvalues and the right eigenvectors. So, do you see my whiteboard, Shabab? Okay.
Yes.
Okay. So this is my matrix. Okay. To find the eigenvalues, we need to solve the equation that the determinant of S minus lambda I equals 0. Am I right? So we're basically solving the following equation, where what is S minus lambda I here? It's going to be 2 minus lambda, 1, 1, 2 minus lambda. Am I right? This is the matrix we're trying to compute, to which we're trying to compute the determinant g equal to 0. So if you take the determinant here, for sure you get 2 minus lambda squared minus 1 equals 0, which means you should have something of this kind. You should have 4 minus 4 lambda plus lambda squared minus 1 equal to 0. So basically solving second degree equation which is lambda square minus 4 lambda plus 3 equal to 0. Okay? And I always say to my students, here when you have a plus b plus c equals 0, for sure, one of the roots is equal to 1. Okay? And the remaining root is c over a, which is 3. So basically, these are my two eigenvalues. Are you okay with this, Shabab? I was saying that when you have a second degree equation, ax squared plus bx plus c equals 0, if it happens that a plus b plus c equals 0, in that condition, in that case, well, the roots are quite easy to find. It means that you have two solutions, x1 equals 1, and the second one is x2 equals c over a. And this is one of these cases. Okay, so for example, here lambda 1 equals 1, and the next one would be 3 over 1. Okay, so these are the two eigenvalues. Is that clear, Shabab? Yes, Abdullah. Abdullah.
Doctor, shouldn't it be -1 and -3?
Check -1 if it works. If you place -1 here, what do you get? Yeah, Abdullah? You get 1 plus 4, huh?
No. -1 -3 will get -4, and then we multiply them and we get +3. Because the b is minus here.
The b is, look, Abdullah, if you place -1, -4 times -1, how much it gives you?
4.
4. And don't forget, you have a lambda square here. Okay? So you should have, you place 1 plus 4. How much is that? 5 plus 3 is 8. There's no way it can be equal to 0.
Okay.
Maya, okay?
Yeah.
So the roots are lambda 1 and lambda 2 here, 1 and 3. Now, to obtain the eigenvectors, which were proposed here in these slides, we said we need to solve this equation that ax should be equal to what? To lambda x. Am I right? So you should take, for example, here in our case, to find the eigenvalue, the eigenvector corresponding to lambda 1, which is 1. You need to find the one, the x1 that satisfies the following condition, the one that says that x times x equals lambda times x. Am I right? I just switched from A to S here. So since your lambda, for example, lambda 1 is 1, basically you're saying which x1 would give me the following. Okay? How many unknowns are in x, in fact? This is, we are working in 2 by 2, so x has 2 components. Let's say you have x1 equals, and without loss of generality, you can call them AB. Okay? So I'm looking for the components AB, such that you will have to multiply S by x1. You will have 2a plus b should be equal to x1, yani should be equal to a, and at the same time you should have a plus 2b equals b. Okay, and if you work on the system, you probably end up with the following solution, basically, which is much. Sure, for sure, there is a one that is positive, the other that one is negative, right? So here, if you work on that, if I'm subtracting from the first row 2 times the second row, I'll get b. I'll get minus 3b, or I can make it more simple. Life's much more simple. I'll have a plus b equal to 0. So, and here again, I have this b plus b equals 0. Okay. So any pair here that satisfies a equals minus b should give me a solution. Okay. So for example, if you place a equals 1, you can conclude that b equals -1. You have infinitely many possibilities here, but one of them would be 1 minus 1. If you wish, minus 1, 1, 2, it works. Okay, this is one way to get the first eigenvector. To get the second eigenvector, I have to place here, instead of lambda 1 equals 1, I have to place lambda 2, and I will obtain the second eigenvector, which is x2. Okay, and here I should insert the 3 instead of the 1. Okay, and things would change, and finally I will get the second eigenvector, which is x2 given by 1, 1, if you wish. Okay, so here I wanted to give you just the general idea on how to get this by hand. So that, I think we did it before, if I'm not wrong, but again, this is one way to get it. The most important thing, Shabab, is not to dive into the complications or the complexity raised when you have more than second degree polynomials to solve. This is not the intention. We said that we have the Python packages that can do this, and in a fraction of a second that can give us the answer. Most important thing is to understand what do they represent geometrically and algebraically, and what the kind of information we can extract from them. Okay, so I'll switch back now to my slides. So again, we were talking about we're talking about this matrix, and we try to go to dive deeper on what do the eigenvalue mean for a matrix. And for example, one can say that we do have what we call the trace of a matrix S. And if you sum up all the eigenvalues, we have the trace of the matrix, what it leaves on the plane, in fact. So here in our case, you can see that the trace is always equal to the sum of the terms in the diagonal. Okay? So for instance, you can check that lambda 1 plus lambda 2 is equal to 4. Now the determinant, once you got the determinant, always equal to the product of the eigenvalues. If once you got the eigenvalues, you can always say that it's the product of the the determinant is the product of the eigenvalues. Now, but in general, you could be possibly finding repeated eigenvalues, complex eigenvalues. So for symmetric matrices, like the one we had before in the previous slide, like the one we worked on the whiteboard, they do have real eigenvalues. And the kind of eigenvectors we can generate are always orthogonal. So if you do satisfy the condition that the two eigenvalues are not equal, then you could generate what we call orthogonal eigenvectors, and which is very important, which means that you could possibly generate an orthogonal matrix from using the eigenvalues, an orthogonal matrix from any matrix, from a given matrix A. Okay, so the rotation matrix Q given by 0, 1, minus 1, 0 here. If you think about it, when you try to solve the determinant of Q minus lambda I equal to 0, will give you two imaginary eigenvalues, which are I and minus I, with corresponding eigenvectors, which are 1 minus I and 1 I. Okay, we can do it together if you wish, or we can just move forward. What do you think, sir? Is it okay? You think you can get it? So basically, when you're trying to find the determinant of Q minus lambda I, here, basically, you are seeking the determinant of R. Very clear? Okay, Hassan. So you get minus lambda, negative 1, 1, and minus lambda. And basically, you're solving the equation lambda squared plus 1 equals 0. One can say why plus 1? Because when you compute the determinant here, you have minus 1. So for sure, you have two roots here. Either lambda equals I or lambda equals minus I. You can proceed as we did with the previous matrix to find the eigenvalues. Okay? So another way to observe that. But moreover, you can see that even for this rotation matrix, we do satisfy all of the 4 properties announced above. First of all, what is the trace? The trace is the sum of the element of the diagonal, right? Am I right? Which is 0. And you can see that the sum of the 2 eigenvalues, I and minus I, is also 0. What about the determinant? Well, the determinant here would be 0 minus 1. So, am I right? So it's plus 1. And again, when you multiply the 2 values by each other, you get 1. You get I times minus I, which is also minus I squared, which is also plus 1. Now, we do not have real eigenvalues. Well, it's not a problem. But we do also have what we can call orthogonality, orthogonal eigenvectors. If you multiply both eigenvectors here, 1 minus I and 1 I, you can get a 0, which means that the 2 eigenvectors again generated are orthogonal. Okay, guys? So we do satisfy these properties, even though the complex eigenvalues were obtained. Now, what about what we call, and this is the last part in section 1.6, and we try to take advantage of these properties to generate what we call a diagonalization of a given matrix. So what we said before is that when we know the eigenvalues and the eigenvectors, we know the matrix. So somehow it's kind of saying like the eigenvalues and the eigenvectors, they give a compression of my matrix. Okay. So the equation that was in general written as x equals lambda x, if you put all the lambdas together in a matrix and all the vectors together, they give me ax equals x lambda here, which is the capital lambda, in fact. And if you multiply both sides by x inverse, we obtain the following. So A in fact is nothing but x times lambda x inverse. Okay? One might observe that this could be only possible if x inverse exists. Well, fine. But let's suppose it exists for now. So for example, if you take this matrix, which could be summarized, in fact, here we're given the 2 eigenvectors, 3, 2, and negative, and 1 minus 1. Okay? The eigenvalues 10 and 5, place it here. And this is the x inverse. We can easily compute our matrix. Right? So we can also easily compute powers if you know this, because powers, as you know, as you see here for a squared, just placing again, for example, if you want to compute x squared, you just add increase the exponent here, or the power for the lambda matrix. Okay? How come? Because if you know that A is equal to x lambda x inverse, and you multiply again by x lambda x inverse, okay, what happens between? This is I, so go, the lambda times the lambda becomes a square, and what you get is just x lambda square x inverse. Okay. So now to come back to this question, when does an invertible x exist, or when does x inverse exist? Well, there are 2 things that signal the existence of x inverse or not. We talked first of all about geometric multiplicity. Well, the geometric multiplicity, what it does, it counts the number of independent eigenvectors. Basically, it looks at the dimension of the null space of A minus lambda I. And there is a corresponding algebraic multiplicity, which counts the repetitions among the eigenvalues. So in general, there is a property that needs to be satisfied. And you think of it as if the geometric multiplicity is strictly less than the algebraic multiplicity, x inverse cannot exist. And then in that case, A is not a diagonalizable matrix. So we have here 3 examples that show that your matrix is not, these 3 matrices cannot be diagonalized. Okay? One of them is quite easy here. For the 5, 5, 0, I shared with you the whiteboard for it. So if you're basically working on this matrix and you would like to check the determinant of A which was 5, 1, 0, so A minus lambda I will give you 5 minus lambda. Here we get a 1, here we get a 0, and 5 minus lambda. So the determinant would just basically be 5 minus lambda squared. Am I right? Yeah. So what are the solutions? Lambda 1 is equal to 5 and lambda 2 equals 5. Am I right? So you have repeated values, which means you have repeated eigenvectors. Okay, guys? For the second one, where the determinant, here again, 6 minus lambda minus 1, 1, 4, minus lambda here. Again, if you work on it, you get 6 minus lambda times 4 minus lambda, and you get a plus 1. So you get, how much is that? 6 minus lambda times 4 minus lambda. And you have a plus 1. So you get with 25, and you get, I think, minus 10 lambda plus lambda squared. So it's again 5 minus lambda squared. Okay? Which means that lambda equals 5 is again a repeated eigenvalue. So you can check that this cannot work for this matrix. Okay? Okay, Shabab? So here we covered all the material we have in 1.6. So one can check also. I'll share with you the application. Hopefully it works. Yes. So here I'm working on my my spectral code, and I'm trying to check that if things could work if I insert one of these matrices. Okay, the one for which that we do have the repeated eigenvalues. So that was 5, 1, and I think it was 0, 5. Okay, so let's see what happens. So this is for the first matrix. So basically, if you remember with this code, we're trying to obtain the eigenvalues and the eigenvectors. Okay. There was a problem here because I didn't change the identity matrix. Should have been here. I think this should work. So Muhammad Abdul Majoud. So you see, here we have the eigenvalues and eigenvectors. Eigenvalues are 5, 5. Eigenvalues and vectors are 1, 0, and 0, 1. And we have the remaining information. Okay, so Muhammad Abdurrahman is here.
Yes.
العزيز
Yes, Dr. Here.
سلطان العبودي، سلطان، خالد البديع،
Yes, yes. Here.
حسن آل بن سعد،
Yes.
إله الفرج،
Yes.
فارس الحسن.
دكتور
Yes.
سلطان العبودي
نعم موجود. فارس موجود. طيب عبد الرحمن الحسين، محمد الجارود،
Yes, I'm here.
عبد الله العريني،
Yes.
ثامر عتيبي.
Yes, doctor.
طيب عبد العزيز راشد،
Yes.
فراس موجود،
Yes.
فراس الرميخاني،
Yes.
عبد الله الرقيعي،
Yes.
حاتم الرويش،
Yes, yes.
نواف الشهري،
Yes, doctor.
فيصل السيد،
Yes, I'm here.
زياد بس،
Yes, here.
يوسف بنتن،
Yes.
عبد الله ضارون،
Yes. Present.
خالد باسودان،
Yes.
ريان كعكي،
Yes, doctor.
محمد سليم. طيب. Okay, guys. So here you go. So don't forget you have homework to submit late night at max on Saturday, and we have an office hour from 12 to 1, inshallah. I will open a room and send you the link just before 12, and send you the link so you can connect and you can ask me a question if you wish. Okay?
Doctor, I did.
So see you there. What is your name?
Abdulaziz.
Abdulaziz?
Yes.
Abdulaziz Sumbul?
Suleimani.
Yes, I know you're here. أي نعم. سليمان. Yes, go ahead.
فارس الحسن.
نعم عبدالعزيز.
Sorry,
can you repeat your name?
فارس الحسن.
Faris Al Hassan, yes, I told you, present. Yes, you're present. Yes.
Thank you.
Okay, have a wonderful day. Anyways, there is an office hour after almost 1 hour. يلا السلام عليكم.